Hi everyone, welcome back to the Mobile Robots Systems course. In this second lecture, we will be talking about robot control architectures. In particular, we will study one running case study, and I'll be showing you how to solve that task with 3 variant control architectures. Without further ado, let's get started. So in this lecture, we will be focusing on the topic of robot control architectures. And what I'd like you to take away from this lecture is that there are 2 very complementary ways of thinking about how to program a robot. So there are deliberative methods, in other words, planning, which I would presume that you're already very familiar with from other concepts and courses in computer science. And there is reactive programming or reactive ways of programming a robot control architecture, which is perhaps a little bit newer to you. And that's why we're going to spend a little bit more time talking about these reactive control paradigms in this lecture. And I will conclude the more theoretical foundations of these control architectures with 3 different examples of how you might implement such schemes. So I'd like to kick off by re-showing you the general overview of the whole course and showing you how the control architectures part fits into this. So as you recall from the introductory lecture, I showed you the control architectures layer is really the glue that brings together all the individual modules that implement the various techniques that we need in order to make a robot autonomous. So today we will be focusing on the different ways that combine the 3 different modules, perception, action, and decision making. In other words, this is what we term or label as a control architecture. So one very important key idea that governs robot autonomy is this idea that the building block of autonomy is a perception action loop that is indefinite. And this is really a key concept that rules basically any robotic system. So the perception action loop is a cycle that allows the robot to essentially cycle between things it perceives and things that it does, right? And in between that, of course, we sandwich the decision-making process. So let me elaborate the perception action loop a little bit more in depth with a couple of examples. So the core idea to the perception action loop is that the robot, an autonomous robot, is in continuous interaction with its environment. And what the robot does is it uses its sensors to perceive what's happening in the environment. What it perceives is something that will allow it to change its internal state. And it perceives this change in the world through its action or because the world is dynamic, right? Then the robot would then process this information to make an informed decision, right? So this is the decision-making module, about what control action it next wants to take. Again, this needs to then be perceived, right? So what the robot ends up doing or what new state it might find itself in or how it has potentially changed the environment. And this is then how we end up in this loop, right? Now, what's important here is that there are different variants to how you could implement the perception action loop. So the first one is the simplest, where it's very simply reactive without any memory, where the next control action is a direct function of the sensor reading. The second variant is reactive with memory, where the next control action is a function of the sensor reading plus some former readings or using some former robot state. And the third method is what we're calling deliberative, where the robot may use all sorts of information that is stored to not only decide upon the next time step action, the action that it will take in the next time step, but perhaps to plan a whole sequence of actions into the future, right? So we can think about this in an analogy with respect to robots that are trying to navigate somewhere, right? So the motion analogy here would be in the first two variants, we're going to take the next step, right? We're going to plan one time step ahead. And the idea with deliberative planning is that we're going to be planning not only one step, but several. So perhaps we're actually planning a path. And what's really key here is that as soon as you start integrating or thinking about longer time spans in the future, these kinds of problems become very interesting and rich optimization problems, right? Because you're trying now not only to think about, okay, what am I going to do in the next time step? How am I going to react? But how can I plan an optimal path, given that I have an idea of what I want to do in the future and I have an idea of how the world is going to unfold itself ahead of me in the future, right? And so you can see here the robotics problem starts becoming very interesting. So what I'd like to do now is another little Gedanken experiment, a little exercise to help you imagine or more deeply understand what the importance is of the perception action loop in robotics. So in this little toy example, let's assume that we have a robot that is on the moon and it would like to do things. Say it's trying to monitor the environment there and it has to move around in order to take a couple of samples. So in order to do this, the robot needs to perceive the terrain and other obstacles. And because the robot does not have enough computational resources, so it's very resource constrained up there on the moon, it sends information back to Earth for processing. And it assumes that it relies on a control station on Earth that then processes this information and sends back to the robot what decision or action it must take, okay? So, for example, the control station on Earth would process information and tell it, okay, based on what you're sending us, you need to now turn left because that's where something interesting lies and that's where you should then go and take a sample. Now, the question that I'm going to ask is how much time passes between control commands, right? And I want you to take a couple of seconds to think about or to compute the answer to this question. Okay, so let's walk through this to the solution to this together, which is very simply computed as far as you can get the key numbers together, right? So the first thing we need to know is how far is the moon from the Earth? And the second thing we need to know is what is the speed of electromagnetic waves, which is the speed at which the information travels. So with these two numbers together, so we have just under 400,000 kilometers for the distance and 3 times 10 to the power of 8 for the speed, so meters per second for the speed of electromagnetic waves. That gives us a round trip travel time of just over 2.5 seconds, right? So what does that round trip travel time mean for our autonomous robot? So if we think that the robot is continuously moving at, say, 10 centimeters per second whilst it's waiting for its next control commands or its next decision making guidance, it actually moves 25 centimeters between control commands. And during that time, during these 25 centimeters of motion, it is actually driving blindly because it's waiting for Earth to send back information based on what it perceived 25 centimeters ago in its path, right? So this means that we need sensors that scope out exactly what is in the 20 centimeter range and, fingers crossed, hoping that nothing unexpected actually happens in that time. Alternatively, the robot can just move much more slowly and hope that within a shorter time range or distance, nothing would indeed happen. So you see, this is a complicated problem, and the perception and action loop plays a big role here. We could, of course, take the same little Gedanken experiment and exacerbate it by thinking, well, we could actually have robots on Mars, where then we'd not have 2.5 seconds between control commands, but actually 6 minutes. And you see this really, the distance here, or the extremity of the environment that we're trying to run these robots in, plays a big role in what we can actually eventually do with robots if we're relying on external autonomy or guided infrastructure-based autonomy for these systems. Right. So now I just want to touch again on the topic of reactive versus deliberative control and summarize the differences of these two different approaches before we deep dive into the reactive paradigms, a couple of the reactive control paradigms. So in reactive control, the control uses a current estimate of the world, where we have time invariant rules to produce an action that is simple and fast to compute, right? And today we'll be focusing on exactly this paradigm, and I'll be introducing to you two different main reactive paradigms, so Braitenberg vehicles and a subsumption architecture. In deliberative control, which lies in stark contrast to reactive control, the predictions of future states are made and relied upon in order to plan sequences of actions, right? And these sequences of actions are planned or constructed in such a way that they optimize some objective. And the designer of these deliberative approaches is free to decide what kind of optimization objective one might want to consider. So you are very well familiar with a couple of such algorithms, for example, the A-star algorithm, right? And we can take these kinds of algorithms and develop analogies that are useful to robotics. For example, if we want the robot to plan a path from A to B, we simply could take a metric saying, I want you to take the shortest path, and then decide based upon some knowledge of what the environment looks like, decide where this path should lead me through, right? And we will talk a little bit more about these deliberative approaches and how they apply to robotics in lecture 6. And I do encourage you, invite you to think a little bit about what the pros and the cons are of these two various approaches as you see more and more of examples of what robotic systems are and what they can do and how they're constrained in real-world environments, and how in some situations we might want to use one control approach versus the other. Okay, so now I'd like to talk about one of my favorite reactive control paradigms. So this one, we already touched upon this very briefly in lecture 1. This control paradigm, this reactive control paradigm, was introduced by Braitenberg, so the neuroscientist who was studying behaviors through reverse engineering. And what Braitenberg did was essentially propose something that we today refer to simply as Braitenberg vehicles. So Braitenberg vehicles rely purely on reactive behavior, where the action relates to the occurrence of an event and does not depend on any state or any memory. So the architecture of these Braitenberg vehicles is termed proximal, which basically means that sensor information or sensor input is very close or even directly connected to the robot's control output. So you could try to imagine what actually happens if I have a sensor and with very little modulation of that sensor information, I connect that information directly to motor inputs, right? What could you do with that thought? What can you do with that kind of construct? And this is how Valentino Braitenberg thought about designing a system that was proximal and reactive. Right. And he took this whole idea of his reactive vehicles and expounded it and described it in a book that he called Vehicles, where he essentially is describing intelligent vehicles using this imagined technology. So he actually himself never built these vehicles, but the thought process was so well designed and developed that he had tremendous impact, and a lot of developers in later years actually went about and designed these actual physical robots and showed that indeed these control paradigms actually work, and the whole paradigm that was thought up or imagined through Braitenberg, it actually holds, it really works. And that was the whole beauty or elegance of the paradigm that Braitenberg designed back in his day. So let's have a look at a Braitenberg vehicle now. So as I mentioned before, these were initially constructed as thought experiments, and the key idea here that Braitenberg came up with was that sensors would directly be connected to the motors of his vehicle, right? So think of how this might be done in an actual living creature. So how he schematized this was as follows. So he designed initially vehicles that had one type of sensor, so light sensors, so sensors that react to light. And he decided that the motors that he wanted to control were simple wheels, so wheels that drive the vehicle, okay? And the key thing here is that he designed there are two components that he could play with. So one was whether a connection from a sensor to the motor would be inhibitory or excitatory, right? So an excitatory connection means the more sensor input, the more that incites the motor to move. And inhibitory, the inverse. And the other element that he played was where he would actually place the sensor versus which motor it would control, right? So you could imagine the sensors being placed as they are, or you could imagine them being, for example, crossed over. So the left sensor being connected to the left motor, or the left sensor being connected to the right motor. Okay, so those are the two design variables that he essentially was playing with. Now let's have look at a couple of examples of Braitenberg vehicles, and I'm going to explain to you a little bit what's going on here. But I would like you in the meantime to think about what kinds of behaviors these Braitenberg vehicles are actually exhibiting. So remember that we have two design variables that we can play with. And the first one is how Braitenberg decides, or how the designer decides to place the sensors with respect to the motors that they're controlling. And this placement will essentially decide upon the difference, the gradient between how the gradient between the sensors affects how the motors are being controlled, right? So we have the symmetry axis in this particular case, a horizontal line that's going across the robot. And the placement of the sensors and the connections that are then made will decide how the robot ends up moving. And the second design variable, again, is our excitatory versus the inhibitory connection that we can make. So let's have a look at the first row, which considers two different excitatory connections. So the very first vehicle, we have the right motor being connected through an excitatory connection to the right sensor, and same with the left sensor and left motor. So if we have a light source that is closer to the right sensor, this means that the right sensor will be excited to a higher degree than the left sensor, right? So the right motor will be excited to a higher degree than the left motor, which means that the robot, as it gets closer and closer to the light source, will start turning away from the light source because the right motor is moving more or faster than the left motor. And so the behavior that this ends up producing is what Braitenberg called a coward type behavior, right? Because the robot is scared of light. Now, if we cross over these sensor connections, right, exploiting the symmetry axis and the difference or the gradient between the sensors, what we end up having is the inverse type behavior, right? So the closer the robot gets to the light source, the more the right-hand side sensor is being activated, and the more that excites the left-hand side motor. So what the robot will end up doing is aggressively moving towards the light source, okay? So this is an aggressive Braitenberg vehicle. And now we can do the same Gedanken experiment with inhibitory connections. And you can now use the same train of thought to think about what these two bottom vehicles would end up doing as they move towards the light source. So in the first case, we have inhibitory on the right-hand side sensor connected to the right-hand side motor, which means that the robot, as it moves closer and closer to the light, it will start orienting itself towards the light, and it'll eventually stop in front of the light because these are inhibitory activation signals that are being passed on to the motors. So the robot will eventually have no speed anymore on its motor. So it will just look at the light in a loving way and stay sitting there. And then if we cross over these connections, the robot will move towards the light, but then it'll move around it as if it were avoiding it as in an obstacle avoidance type motion maneuver, right? And we called, or Braitenberg called this, the explorer type robot. And so you can see here that the key insight here for you, or the takeaway message for you here, is that very simple internal architectures using very simple sensors can already create very interesting and actually quite rich behaviors that you might not have thought are so simple to design had you seen them without knowing what is behind, what is inside this black box of sensor to actuator connections. And another key insight here, and this is what Braitenberg really demonstrated in such an elegant way, is that synthesis is much easier than analysis, right? So you can reverse engineer, try to generate behaviors through very simple paradigms or rules, but had you seen them and tried to analyze how they might come about, you might have had much more trouble in understanding or designing the models that produce these behaviors. Now, Braitenberg vehicles are not only useful to create interesting behavioral or examples, they're also interesting to do useful things. So if we think about a vehicle that we want to control to stay on a road or on a highway, we can use these type of reactive Braitenberg type control schemas to do that for us, right? So if we think of here replacing the light sensors with floor sensors, and we're connecting these light sensors to our two motors on a vehicle, you can do a little exercise on the side and think about, well, how would you connect these two sensors to the motors to make sure that when the robot starts veering off the road, it corrects its motion so that it moves back onto the road, right? So I'll leave that as a small exercise for you to think about. So what I'd like to do next is for us to think about how we can generalize the Braitenberg vehicle and implement it to make it more useful on actual robots and not just imaginary Braitenberg vehicles. So what we want to do ultimately is, assuming that we have a differential drive wheeled robot with two actuators, we want to compute the left and right wheel speeds. And so what we're going to do is we're going to set up a system of equations where we have one known input, which is in this case a set of 8 sensor measurements, right? We have 5 sensors in the front of the robot and 3 facing its back. And the question that we're posing now is, how do we combine the sensor input to produce a useful motor output for both the left and right wheel speeds? And so what we do is we set up matrix multiplication, or a system of equations, where we have essentially one equation for the left wheel and one equation for the right wheel speed. So if we look at the system of equations, we have our alphas. On the top row, these alphas correspond to the weights that we're multiplying the distance measurements with, right? So alpha 0 to alpha 7 multiply distance measurement 0 to distance measurement 7. And we do the same for the right hand wheel speed, right? So alpha R0 to alpha R7 again multiplies the same input incoming sensor measurements. We add a base forwards velocity. So this is a bias speed, which is in particular useful when we consider these weights to be inhibitory connections of our of this connection of sensors to motor output. So now the question that we're left with is, how do we actually compute these weights? So for a system which is composed of only 8 sensors and 2 final outputs, we can conceivably do this by hand, by tuning them, by making an informed guess, and then having a look at how a robot, for example, in simulation performs with respect to these given tuned weights. And indeed, this is what many people do. What we will look at now in the next slide is how we might actually generalize this to an even more powerful system. So here, we're actually taking the Braitenberg controller that we generalized before to a linear combination of weights to produce output speeds, whereby the linear combination is useful and certainly very practical in many cases, but actually nonlinear combinations are more powerful. And the idea of implementing a Braitenberg type controller in a nonlinear form is ultimately what we aim or what we want to do. So here, what we're doing, instead of having sensors connected to actuators directly, we're going to create a neural network architecture, so an artificial neural network, where the sensor input feeds into neurons. And here we have two neurons. The reason we have two neurons is because we have two outputs. So we have two motors that we want to actuate and control. So we're going to have an intermediary step of feeding some input into the neurons, and the neurons will then feed some output into these motors. Okay. So going through this step by step, again, we have 8 sensors and 2 motors. And internally, we have 2 neurons. The neurons will take an input value X and will transform this input value to an output O. Again, we'll assume that our sensors have inhibitory connections, so the weights here are negative. And we will add a bias as an excitatory connection, or to give us some basic bias forward speed, right? So that our robot does not actually stop if the sensor input is telling it not to move forward. In the image, the line thickness that connects the sensors to the neurons could, for example, represent to the weights. So sensors that are connected with thicker lines signify that these sensors are more important. And this does make sense because if you look at the image, the sensors that are facing the front of the robot tend to have a little bit more importance because that is generally the direction that the robots head in, and those are the contact points or the obstacles it would make contact with first in the case of collisions. And so we have 2 neurons where each neuron will take in a linear combination of the sensor input. And this is the equation that you can see on the left-hand side of the panel where we're summing up for J1 to M, where Wij is indexing sensors and neurons, Ij is our incoming sensor information, and I0 is our bias forward speed. And these neurons then output we'll take this linear combination and they will output a nonlinear transformation of this input X. So what is the nonlinear transformation to be? Well, there are many options for this, and one example, the one that I'm showing you here, would be to take the hyperbolic tangent, which functions similarly to a sigmoid. It goes from -1 to 1. And this is interesting because you can then scale or normalize this the support on the y-axis by the maximum wheel speed, for example, right? Now, this brings us to, this kind of completes the full neural network architecture. So we are going from sensor input to motor, to the input to the motors through first a linear combination and then a nonlinear transform. And the only thing that we are left to do now is to find these weights W subscript Ij. And the question here is, well, how are we going to do this? It's not as trivial because of the nonlinear transform that we have sandwiched in the middle of all of this, but you might recall the form of these equations from introductory lectures you've had on neural networks and artificial intelligence. And so the answer, there are many ways of actually optimizing for these weights, and you will find a lot of different methods that would allow you to do this by looking into the methodologies of estimating or inferring or regressing over these values to find the weights that you need in order to achieve a certain performance. And so here we're really connecting to the field of machine learning, and you saw this happen over a step of just 3 slides, starting with a very, very simple Braitenberg controller connected just by 2 sensors to 2 motors, to suddenly a system that is not that much more complicated by just introducing 2 neurons in the internal architecture of the robot's logic. So now we've seen a couple of examples of how to connect sensor input directly to an actuator, to its output. But the behaviors that are generated in this way are extremely simplistic. And ultimately, we know that more complicated behaviors will require more sophisticated control architectures. And in order to do this, we have to come back to our original idea of implementing individual perception, plan, and action modules, and thinking of the control architectures as the glue or as the framework that allow us to combine these modules at a higher level. So what we're going to do is we're going to look at 3 classical examples of control architectures that allow us to do this. So we're going to look at a finite state machine. We're going to look at an architecture that was coined as the Subsumption Architecture. And we're going to look at sense, plan, act as well. And we're going to look at these 3 architectures on the hand of one running case study, which is called Pick Up the Trash, which was a AAAI competition that was run over 2 years in the 90s. And in this competition, it was a very simple proposition. Robots had grippers, and they were supposed to collect soda cans, which were red, and bring them and throw them away into blue rubbish bins, right? So these robots had to explore an area, identify the location of red soda cans, pick them up, and identify the location of blue rubbish bins, and then bring these cans and drop them into those rubbish bins. Okay. And what we're going to look at now is how do these control architectures in their own way implement this kind of behavior. So let's start by looking at what finite state machines are. Right, so before we looked at Braitenberg vehicles, which operate on current input values only. So what finite state machines do is they add the capability of state. So the robot is capable of remembering what state it is in. And this turns out to be quite useful, right? So in this particular case of control architecture, we're looking at a finite set of states and transitions between these states. And the logic that connects these different states is really what decides or defines how the robot would behave in a given environment or setting. So a very simple example, we can look at a toaster, for example, which by default would be off, right? So the toaster is always off. If the toaster detects that its lever is pulled down, then it'll turn its heat on, in which case it'll transition into a state where it knows it's on. And in that state, it will trigger a timer. And if that timer expires, the toaster knows it has to turn its heat off again, at which moment in time it goes back into its default state, which is off. And this is the life of a toaster. So very simple, and you can represent it concisely with this finite state machine. So now let's look at a little bit more of an involved example in the case of a robot. So this particular finite state machine is representing a robot that has as a task just to explore an environment. By default, we could assume that the robot is in a random walk, so just randomly is moving around an environment. If the robot finds an object, it will transition into a state that tells it to inspect this object. It might, for example, look at what is the color of this object. Once it determines that this inspection is finished, it is satisfied, it will transition back into a random walk state. However, if it encounters an obstacle, it will then transition to an avoid state. It'll avoid this obstacle and then transition back into the random walk state. So here we have perception modules, which in this particular FSM are represented by the transitions from state to state. The states themselves actually are actions, right? So random walk, inspect object, and avoid obstacle. These are 3 actions. And the whole schema here, the way the perception and action state or elements are connected together, that is the decision-making logic, or that is the decision-making paradigm of this FSM. Right. Okay, so now let's move on to our running example of picking up the trash, and let's see how we would implement an FSM for the pick up trash example. So let's assume that in a default state, the robot would be wandering for trash. So that's the very first state on the top left-hand corner of this panel. If the robot detects that its gripper is empty, so it's capable of picking up trash, and it sees something red, right, because our trash is red, the soda cans are red, then it'll move to the trash. It'll move towards the soda cans. If the gripper is still empty and it detects that it's standing right in front of the soda can, it'll try to grab it, okay? If it then detects that the gripper is full, which means the soda can was successfully picked up, it'll then wander around trying to find the rubbish bin. If the gripper is still full and it sees the rubbish bin because it's seeing something blue, it'll move directed towards that rubbish bin. If its gripper is still full and it's located at the rubbish bin, it'll then open the gripper, drop the trash into the bin, and at that state, we're hoping that the gripper is empty, and we get back into our default state, which is let's wander around for more trash, right? So this seems to be very straightforward and seems to cover everything that the robot needs to do in order to solve the task. Now, the problem is that there are many additional cases that we have to think about, and we also have to model them in this finite state machine. Just a couple of examples would be, for example, what happens if the robot is not able to grip correctly, right? So it's trying to grab the trash, but the grippers are sleepy or the soda can is still wet. Well, we could say, well, we'll give it 3 tries. And hopefully after 3 tries, the gripper is then full, but maybe it isn't full and then the gripper is still empty. Well, we're just going to have to give up that particular trash piece and go back into the state where it's wandering for trash. Another thing that could happen is that the robot is carrying the soda can and it's now wandering or has found the bin, but possibly the soda can slipped through the gripper during the motion, and before it actually gets to the bin, the robot has lost the soda can. So if the gripper is empty by the time the robot gets to the soda can, there's nothing to drop. So we need to include a transition that allows the robot to go back into the wander state without trying to drop the trash, right? And there are many, many more cases that we would need to model here to really exhaustively capture all the failure scenarios or alternative scenarios that conceivably can really happen in this relatively simple task of picking up the trash. So you can already tell that constructing finite state machines as our control architectures is very complicated and perhaps not particularly elegant unless we know or we are very confident that we can exhaustively enumerate all the possible states that our world may throw at the robot. So now let's move forwards and think about what different general paradigms we could use in order to implement control architectures. And I'm alluding a little bit to some of the ideas I mentioned to you in the introductory lecture to this course, where I talked about serial architectures, so performing things in sequence, versus concurrent behaviors, so not doing things in series or not thinking about doing things in series. And there's this real dichotomy in architecture design that came about in the early 80s when we realized that AI or classical planning algorithms were perhaps not all we hoped they would be. So in serial architectures, these systems are very straightforward in the sense that we have our sensors on one end, we have the actuators on the other end, and we have all these other logic modules that we can implement and sandwich between the perception and action modules, right? So the whole planning bit of the problem. Now, the other way to think about this is that we can actually have several behavioral processes running concurrently, right? So why not have all sorts of different types of sensors running concurrently, and each sensor knows what it might want to do or knows what it has to trigger upon a certain trigger event or a certain input that means something to that sensor, right? And the key thing here is that since only one action can effectively be executed by the main motors of the robot you're trying to control, we're really left with 2 choices, right? So we can either prioritize what our sensors are telling us to do, right? We're telling, well, at this point in time, that sensor seems to have more importance given the input or the information that I have, and tell other sensors to basically take a step back and give that sensor priority in what it's saying the decision or the control action should be. And the second option, or the second choice we're left with, is to say, well, we might not necessarily strictly have to prioritize, but we might be able to combine the recommendations of these sensors to produce action commands that are some joint behavior of some joint computation of the sensor output, right? So we can, just summarizing that, we can either prioritize or we can combine. And there are actually 2 control architectures that do exactly that. And so the one I'm going to talk about today is the one that prioritizes. And how we're going to do that is we're going to look at how we can actually hardwire between various processes to decide which will effectively be the one that's sending commands to the motors. And so this idea is exactly the idea that Rodney Brooks had when he proposed his subsumption architecture. So this was at the time a really radical new idea, this idea of concurrent behavior. So Rodney Brooks was at the time a researcher, faculty member at MIT, and in 1986 he published an article called A Robust Layered Control System for a Mobile Robot. And it had an enormous impact. So it has over 11,000 citations to date, or even more in the meantime. And Rodney Brooks really was seen as a revolutionary in the field of robotics due to the paradigm shift that occurred after he published that paper and that line of work that he was currently working on. Right? In a certain sense, it is really inspired by the work that Braitenberg had done, but Brooks was the one that actually went ahead and implemented this not only in simulation software, but on actual physical robots in hardware, where he implemented all the hardwiring, all the processes, and all the logic that was necessary in order to make robots to actually do interesting things. Okay? So what it builds on is that robots have several behavioral modules, so basic behaviors. And each basic behavior, we can assume, is represented by an augmented finite state machine. And the other two key points about the subsumption architecture are that the response to the sensor input is actually predominantly rule-based, so discrete. And the coordination of behaviors is priority-based, right? So it's not combination-based, but priority-based. And the mechanisms that Rodney Brooks proposed in order to do this is via inhibition and suppression. And so that's really key, because this idea of inhibition and suppression allowed him to build up a kind of a hierarchy of behaviors where you might have the most important ones in the bottom and the least important ones in the top, and you can in that way construct what hierarchy or what kind of inhibition mechanisms you would like to see happening in case of a cascade of rules being triggered. Right? So that is the key of this control architecture. So let's have a look at what this control architecture actually looks like. So the schemas that represent the subsumption architecture look as follows. So in this graphic here, what you're seeing is in the center we have a behavioral module. And this behavioral module is driven by certain inputs, and it will produce certain outputs. Now, the key elements here are the inhibitor and the suppressor signals. So the inhibitor signal is basically a connection that when activated, it will inhibit that input to the behavioral module. Right? So if the behavioral module is expecting a certain input and doesn't receive it, it's because that inhibitor signal was activated, right? And it comes from another module. Now, at the output side, on the output side of things, we have the suppressor, which simply can suppress an output of a behavioral module with a different behavioral output coming from a different behavioral module, right? And so these two components here are really the key components that allow the control architecture to do a couple of very powerful things. Now, the other key element or design choice that we have to include here is this idea of hierarchy that I introduced or alluded to just in the previous slide. So if we think of layers at the very bottom as being the more fundamental layers, implementing like the most basic behaviors that you want your robot to be performing, like always, then we can think of layering up more and more sophisticated or articulated behaviors as we increase the layer numbers going from the bottom to the top. And here the key idea is that higher levels can, if they want to, subsume the roles of lower levels when they wish to take control. And if they don't wish to take control, then we have our lower levels just doing their thing, right? And the key here is that all of these behaviors or modules are running concurrently, they're running independently, and they're running asynchronously. And these are really key insights because it allows you to build these systems and hardwire them in a very straightforward way by just simply connecting processors and actuators without having to think too much about how the timing is going to happen All you need to think about is whether or not the logic of how you're hardwiring them, if that is correct or not, and if that will lead you to the correct behavior that you wish or you desire your robot to do. And that will be guaranteed to you by the design of the subsumption architecture. Okay. So before moving on to our running case study of picking up the trash, I just want to go through one very simple example that shows you how to implement a simple two-layer system for a basic behavior. So what I'm showing you here is layer 0 of a given behavior that, if implemented, allows the robot to simply exist in planar space safely. So the robot won't collide with any obstacles. So how does this layer 0 work? So there are several behaviors or subroutines that are implemented. These are contained in the boxes, and they're connected by outputs, essentially, or executed actions. So let's have a look at how this all works. So the sonar module at the very left takes a vector of sonar readings, filters them for invalid readings, and then effectively produces a robot-centered map of obstacles and polar coordinates. Okay? This map is then fed to both collide and field force modules. The collide module monitors the sonar map, and if it detects an object straight ahead of the robot, it sends a signal on the halt line to the motor module, essentially telling the robot to stop. The collide module then, it doesn't really know or care about whether the robot is moving, and at the same time, halt messages that are sent when the robot is stationary don't have any effect. Okay. The field force module sums up the results of considering each detected object as a repulsive force, and it generates or it outputs one single resultant force. So you could think of combining various vectors pointing in different directions, each vector kind of avoiding different obstacles, and the resultant vector would generally point into a force direction that is valid and leads the robot into a valid direction. And the runaway module is key here because it monitors this force vector or force direction produced by the sonar detected obstacles and sends the command to the motor module if it ever becomes significant. Okay. So this layer 0, what it does, it just makes sure that our robot survives as it exists in planar space by not coming into contact or bumping into any other objects. Now we're going to add one more layer of sophistication to this, which does nothing much in addition, but gives the robot a little bit more sophistication. So at level 1, we have a wander module that generates a new heading for the robot roughly every 10 seconds or so. And maybe these directions are directions that the robot is getting from an operator, or it has an idea of where it should be heading and gives it a more directed or targeted type of behavior. So what this wander module does is it outputs the heading, which is input to an avoid module that takes this result, as well as the result from the force computation at the 0th level, and combines it to produce a modified heading, which usually would point roughly in the right direction, right? So it's heading in where the robot would actually like to head into, but it's also combining information about their surrounding obstacles in this map. Now, this computation implicitly is subsuming the computation of the runaway module in the case that there is also a heading to consider. And in fact, the output of the avoid module suppresses the output from the runaway module as it enters the motor module. And by avoiding this avoid signal is actually much more sophisticated than the runaway signal, since it suppresses it when it's available. So what you can see here happening is that the level 1 that we added to this whole system allows the robot to explore. It allows the robot to wander around without colliding into anything, which was then previously guaranteed to the robot by the layer 0 behaviors. And so this is how you can add on capabilities and intelligence to the robot by introducing higher levels with a little bit more sophistication in their design. So now I'd like to give you an example of how we would implement our pickup trash example or running case study with the subsumption architecture. So at the very bottom of our panel here, we have our layer 0, which is, we have a wander module, which is the robot is just wandering around looking for things. And the wander module outputs a heading, so a direction of motion. And this is what goes into the robot's essentially actuator, which is a turning direction, so a heading. Now, moving up from layer 0, we start adding logic. So if a can is detected, this will suppress the wander signal, right? Because we're now not going to wander, we're going to move towards the can. Adding more logic, if the robot knows, if the module, the behavior that is checking for the gripper status, if it detects that it's full, then this obviously must inhibit the behavior that moves towards a can, because we can't pick up a can if we're already holding a can, right? So that's why we have an inhibitor at this layer. Now, if a bin is detected, then this will suppress all layer 0 and layer 1, unless it's inhibited by an inhibitor that says that the gripper is empty, right? Because if there's nothing there, then we don't need to suppress the other two. And at the very top layer, we have a behavior that says that the robot will drop a can, which, by following the same rationale, will suppress and inhibit signals as before. So you can see here we have all these modules or behaviors that are functioning or operating concurrently and are simply connected by status updates, an inhibitor and suppressor signals to ultimately result in a relatively complex or sophisticated behavior that allows us to solve a relatively interesting task of searching for, picking up and removing trash. And what I'd like to do now is, because Rodney Brooks is quite a figure in robotics until this date, I would like to show you a little video that was taken at the time that really has him speaking in his own words about the work that he was doing, and will really show you a little bit of what was going on behind the doors of his research lab.
Robotics, which mimics the behavior of creatures at the bottom of the food chain.
Back in the early 80s, robots were very, very slow. They were connected to mainframe computers. They would compute for minutes at a time before the robot could move even a meter. And if anything changed in the world in the meantime, they were completely lost what was going on. And I looked around at insects, and insects, could fly around at a meter or so per second. They could avoid getting eaten by a bird. They could chase prey that they were after. They could go through mating behaviors. So it seemed to me that maybe we're organizing computation the wrong way, in the way we're approaching robots. And that maybe by trying to organize the computation a little more like it's organized in insects, we would get much better performance.
Brooks' insect robots aren't intelligent the way we think of humans or even computers as being. Instead, they operate on patterns of behavior. When you turn them on, they're brainless. But with each step they take, they learn how to adapt to their environments. Rather than having a standard central controller, these robots have separate layers of behaviors that are independent but which communicate. No advanced behavior can start unless the simpler ones are up and running.
When I first started talking about these ideas, the only good thing going for me was I had videotapes of robots really doing things that other robots weren't doing. Otherwise, it would have been dismissed as a total flake, and probably would have been a total flake. But because I had some performance, people looked at it and thought, well, maybe there's something there, but there was still a lot of arguments from me and a lot of resistance. Now, over time, people who actually build robots have generally come to accept this approach at the low-level aspects of controlling a robot, and it's become the standard way to operate.
Unlike Whittaker, Brooks is not an engineer. His specialty is building brains. The robot's bodies are made by his colleagues and students at MIT. But like Whittaker, Brooks is ambitious and not opposed to making money.
Yes.
Brooks is now chairman of IS Robotics, the bottom-up version of Red Zone.
Ready? How are the new tracks going?
I guess
Virtually everyone on staff is an MIT alumnus. They all share the dream of putting a robot in every living room.
this week or next week we'll get that set.
But right now, many of their robots are paid for by the people who brought you duct tape and the internet, the United States military. The IS concept is to build swarms of small, inexpensive robots that can cover terrain too dangerous for troops to enter. This minesweeper is designed to be carried by soldiers into combat zones. The controls are strictly supervisory. The machine finds its way through the world in the same brainless fashion as Brooks' insect robots. Ariel is an underwater minesweeper built for the Navy. The idea is that before soldiers hit the beach, dozens of these robots will march in and sacrifice themselves on enemy booby traps. Ariel's body was based on a crab. If currents throw it about, it can operate upside down. IS also sells versions of the Genghis robot to labs around the world. The original Genghis launched the insect robot revolution. It was built by Colin Angle, a one-time grad student of Brooks who is now head of IS. Angle and Brooks believe the entertainment market could provide the monetary push that commercial robotics needs. Much as computer games helped finance the microprocessor boom, a must-have robot toy could fuel.
Right, so much for Rodney Brooks. And I'd like to just conclude my narrative of the three control architectures by completing it with the third variant that I mentioned earlier on, which is the classical paradigm of serial or deliberative sense, plan, act. So here, in contrast to what Brooks is proposing, perception and action are aligned serially, and we wedge in the planning module. So essentially, the robot will plan not only the next action, but a whole series of actions, right? So if we look at our pick up the trash example, how would we construct sensible logic for each of these three different modules? So let's think of the perception module. Everything that needs to be done is, for example, we need to position all of the cans, we need to position the trash can, we need to position all the obstacles, and we need to know where the robot is, right? And this is built on the assumption or the requirement that the model of this world is complete and error-free, right? So we need what we perceive to correspond to the reality, and we need the world to be static. So we can't, if we're not rebuilding our perception module continuously, or for example concurrently, the world needs to be static. In the planning component, given that we know where all the trash cans are and where the rubbish bin is, given that we know where the robot is, all we need to do is input that into a planning algorithm that then outputs an optimal sequence. For example, a path that leads through all of the positions of the cans and ends up at the trash can in minimal time, right? So this could be what the planning module does for us. And finally, we feed that plan to our actuators that would then generate a continuous path that is feasible given the robot's motion constraints, leading from one can location to another, generating gripper motion commands, and ultimately ending up in front of the rubbish bin and emptying the gripper for each can that was found and picked up. Okay, so this is our sense, plan, act version of the pick up the trash example. But what's really important here is that you realize that if we're functioning in this sequential manner, we're making a lot of assumptions that we have to be careful about. So if we construct a world map, if our perception module happens once in the beginning and then never again, we need nothing to change, no information to come in that's relevant at any other given point in time. So the world needs to be static and the model has to be complete. So There are a couple of interesting questions we could ask at this point, and I think you might have come up with these questions during the lecture, during my speaking. Well, which one seems to be more useful? Which one seems to be more robust? And there is no clear-cut answer to this, so possibly one could argue that concurrent behaviors are more robust, but they're probably not quite as sophisticated because we can't necessarily optimize for the plan, right? Because we're not solving optimization problems explicitly, which we can do with the Sense Plan Act module. However, the Sense Plan Act module makes a lot of assumptions and has requirements that if we break these requirements, then we're not even necessarily optimal. We're probably even doing things that pragmatically or practically have no meaning or make no sense. So we have to be very careful about what it is that we want to achieve and what the bounds on the behaviors are that we're willing to accommodate. So finally, let's just list these considerations that we need to take into account when we're making the choice of a control architecture. So clearly the first thing we're thinking of is we have to ask ourselves what the application is. Is it a safety application or is it an entertainment application? What is important or what is the priority for our specific application? Are we operating robots that are in the vicinity of humans, or are we operating robots in the wild where it's not too bad if they do funky things from time to time? So these various details do make a difference to what kinds of control architectures we might want to deploy. Sub-questions or additional questions or tangential questions include, do we need parallel behaviors? Is the environment extremely dynamic, or is it completely well modeled and static? Is it important to be robust, or can we afford failure from time to time? Is it important to be very nimble and quick and real time? What is the importance of computational complexity? Is it important that we have robots that are fast and reactive versus perhaps more slow, thoughtful, and deliberative? And finally, is it important that we can predict what the robots are going to do? Do we need proofs and guarantees of what actions robots would take in certain actions? And this is definitely the aspect that is important for many of robot applications to date when we're thinking of traffic and human-robot interaction, where these questions are really paramount. So before concluding with just a few more slides, I want to point out that there are other classical paradigms I didn't talk about today, which you will encounter potentially in your mini projects or in the exercise sessions. One of them is the motor schema paradigm proposed by Ron Arkin in '89. And another scheme is the potential field paradigm that we'll talk briefly about in lecture 6 and you will see in one of your assignments, right? So what are the current trends in control architectures? So clearly what I introduced to you today were some of the foundational control architectures, some of the earliest ways that researchers and developers were thinking about how to control robots with. Now today the trends have shifted somewhat, and one of the most popular ways of thinking about control architectures is by actually going away and neglecting this idea of having a principled architecture by prioritizing architectures that are simple to construct through black box models and connect perception to actuation in an end-to-end architecture, in an end-to-end paradigm. So end-to-end mechanisms are especially relevant or especially interesting when you're thinking of data-driven approaches. So these are very close to some of the things I showed you with the neural network architectures. They can be very proximal in the sense that inputs are very closely connected to outputs, and we might have nonlinear transforms in between them, but they are indeed black box. So we don't, even though we're doing end-to-end mechanisms, we don't necessarily have the capabilities of understanding what the transforms are really doing and how some of these transforms might operate in given robot states, right? So the key idea behind these end-to-end mechanisms that we can actually learn very complex mappings without having to develop them by hand or designing them through human effort, right? And that is why they're extremely popular and attractive. We can leverage large volumes of task-specific data to optimize the weights that are part of these black box architectures, so essentially outsourcing the hard work to simple regression tasks. And we can also leverage the abstraction capabilities afforded to us by deep neural networks, essentially relying on them to not only learn how to map complex sense to act behaviors, but also learn how to aggregate some of these mappings to create perhaps classes of behaviors, because this is what our deep neural networks are capable of doing. They're capable of learning patterns in input data, so what the robot is seeing, to mapping them to a couple of key behaviors potentially. So those are the attractive components, or the reasons why a lot of people have been interested in exploiting end-to-end mechanisms through data-driven approaches. So clearly there are lots of challenges involved with this, and I will talk about these things more at the end of this course. One of the challenges is, well, where are we actually going to get the training data from? So in order to train complex behaviors, we need a lot of data. And collecting this data is difficult, especially because collecting data in simulation does not necessarily correspond to the robot's actual, what the robot will actually experience when it's deployed in the real world. And these discrepancies can lead to catastrophic outcomes. Also, and this relates to this question, is if we train a robot based on data that was collected in a given environment, how does that behavior, how does that mapping from input to control output translate when we deploy the robot in a slightly different environment? And it can be as simple as, well, we trained the car to drive in sunny weather, and then we use that same behavior to train it in an environment where it was foggy. And you might find that the mapping that the sensors learned, or the control the control architecture, the control mechanism learned for us, is absolutely not transferable due to some idiosyncrasies that are baked into this black box model and we cannot isolate. And again, given the fact that we have this trouble in collecting a lot of data from the real world in real time, because physical reality is limited by what humans can actually do in real time, a lot of people have been leveraging training in simulation and then trying to transfer that to reality, but there is a sim to real gap. And challenging that sim to real gap, or trying to reduce it to make these transitions tractable, is one of the most important research thrusts in the field of robotics to date. So with this, I just would like to leave you with a couple of pointers to interesting papers and books, and some. I'm also listing some of the seminal papers I invite you to have a look at. And with this, I leave you with this slide, and I look forward to talking to you again in the following lecture, Lecture 3.